Video in learning target 6A. So in our prior two videos, we've learned how to solve systems of equations by graphing and then how to solve systems of equations by substitution. In this video, we will learn how to solve a system of linear equations by elimination. So we have some steps on how to solve a system of equations by elimination. As we read through them, we're going to walk through the first example at the same time. So our first step with any elimination problem is we want to decide what variable we're trying to eliminate. So do we want to eliminate the x's? Do we want to eliminate the y's? It actually doesn't matter. It's just a choice that we have to make. And by eliminating them, what that means is they should cancel out completely and I should either end up with no more x's or no more y's. To do that, what we're going to do is we're going to add the two equations together. So to get variables to eliminate, we need their coefficients to be opposite numbers then. So for example, 2 and -2 would be opposite numbers because if I add them together, I get 0. 5 and -5 would also be opposites. -3 and +3 are also opposite numbers. So we're looking for numbers that have the same absolute value, but one is positive and one is negative. So let's look at our first example here. We have the system x plus y equals 4. And 2x minus y equals 2. The first thing I want to think about is before I decide if I'm eliminating x or y, I want to look at the coefficients and say, do I have any two that are opposites? So in this case, I have a 1 and a 2 on the x's. Those coefficients are not opposites. On the y's, we have a +1 and a -1, and those numbers are opposites because 1 plus a -1 is going to give me 0. So my goal here is I'm going to eliminate then the y's. That's what I've now decided to do. Sorry, that was an n. I want to eliminate the y's since their coefficients are opposites. So to do that, I'm going to add the two equations together. I'm going to just rewrite both of them. So we have the two equations stacked on top of each other. The other thing we want to pay attention to is it's helpful to have them both in standard form. Now they technically don't need to be in standard form, but they both need to be in the same form. So they're either both in standard form or both in slope-intercept form. But I can't have one in slope-intercept and one in standard form. It won't work. The reason being is I need to make sure the x's line up, the y's line up, the equal signs line up, that's key, and the numbers line up. Well, both of these equations are in standard form, so I can go ahead and add them together. So I'm going to add like terms. So I can add the x's together. X plus 2x will give me 3x. I can add the y's together. Remember, we want to eliminate the y's, which means the y's should go down to 0. If they don't, then we did not set this up correctly. So positive y minus y will give me 0y then. Now I don't need to write the 0y. That looks kind of silly. I'm just leaving it there for the first example just so that we can see it. I'm also going to add together the constant terms. So 4 plus 2 will give me 6. Now again, there's no need to really write the 0y. You could go straight to writing 3x equals 6. I've done this correctly now. I'm not done solving yet, but I've done my first step correctly because I eliminated the variable that I set out to eliminate. So my goal was to eliminate the y's, and they completely canceled each other out. And I just get left with an equation here that's all in terms of x. So that's what step 1 is all about. Now step 2 says solve our new equation for the variable that's left. So this is my new equation down here. This 3x equals 6. So I'm going to solve this for x. To do that, I divide by 3 and I get x equals 2. Now that I have x solved for, my next step is to substitute that answer into one of the two original equations. It does not matter which equation we use, we get to pick. I'm going to go ahead and use the first equation. Why not? So I have x plus y equals 4, and I want to substitute in x equals 2 into that equation. I will then end up with 2 in place of the x, so I'll get 2 plus y equals 4 then. I can now solve this for y. I can subtract 2 and I end up with y equals 2. Just like in our prior two videos, our final answers do need to be coordinate pairs, so I want to make sure that I have my x and my y values written in the coordinate pairs, and that will be our final answer. Now example 1 was set up really nicely so that the y's could kind of automatically eliminate. I already had one positive one and one negative one. And in some examples that does work that way. In other examples, as we see, we might have to do a little bit of extra work so that we have two variables that have opposite coefficients. Let's look at example 2. So example 2 says 2x plus 5y equals 17 and 6x minus 5y equals negative 9. Is there a variable right now that's set up to nicely eliminate? If so, which variable? So what I notice is that it's actually nice to eliminate the y's right away because I have a positive 5y and a negative 5y. So if I add these together, they would cancel each other out. Let's go ahead and rewrite these equations and we'll add them together. Oops, y, there we go, equals negative 9. So I can go ahead and add these together right away. I do want to kind of write a side note over here that my goal is to eliminate the y's, so I keep that in the back of my mind. The reason I'm doing that is because the positive 5y and the negative 5y will cancel when I add these two equations together. The other thing I have to make sure of is that both equations are in the same form, and in this case, yes, they're both in standard form, so I am good to go. When I add the x's, I end up getting 8x. The y's end up canceling out completely, so I end up with 0 y's. And then on the right side, 17 minus 9 will give me 8. From here, we can solve for x by dividing through by 8, and we get x is equal to 1. I'm going to already start keeping track of my final answer over here so that I remember to write it as a coordinate pair, and we know that that x value is already equal to 1. Our next step from here is to pick one of the two equations that we started with and substitute in x to get our y value. It doesn't matter which one we use, I'm going to just go ahead and use the first equation. So we get 2x plus 5y equals 17, and I want to substitute in x equals 1 into this equation. So I'll sub in an x, a 1 right there for the x. When we do that, we get 2 times our 1 plus the 5y equals 17 still. As I simplify stuff down, 2 times 1 is 2. The rest of it stays the same. From here I can subtract 2 from both sides and I get 5y equals 15. The last step would be to divide through by 5 and we get y is equal to positive 3. Now that we have that y coordinate, I can go ahead and fill that in our coordinate pair, and we have our final answer. So in both our first two examples, it worked out nicely that the problem was already set up so that I had a variable that I could eliminate by immediately adding the two equations together. In our third example here, we have x plus 2y equals 3, and x minus y equals positive 6. Right now, as it stands, is there a variable that I can eliminate because I have opposite coefficients? So in this case, I don't have a variable that I can eliminate right away, but what I could do is I could multiply the bottom equation through by a negative 1. And in doing so, what ends up happening then is the top equation stays the same. The bottom equation becomes negative x plus y equals negative 6. So I have to make sure that I multiply every single piece in that equation through by our negative 1. From here, I now have opposite coefficients on the x's this time. So I can go ahead, and my goal right now is I'm going to eliminate the x's instead in this equation. I can add these two together. The x's cancel out since x minus x will give me 0, so those guys cancel. 2y plus y will give me 3y, and then 3 minus 6 will give me a negative 3. Next, to solve for y, I can divide through by 3, and I get y equals negative 1. I can write my coordinate pair so that I'm already ready to go with my final answer, and I'll put negative 1 in the y spot. The next step to do is to pick one of the two original equations and substitute in y equals negative 1. So I'm going to use the first one. So x plus 2y equals 3. And I'm going to substitute in -1 for the y value. When we do that, we get x plus 2 times our -1 equals the 3. I can then solve for x, and I get x minus 2 equals 3. Add 2 to the other side, and we get x equals 5. Filling in our coordinate pair, I then have my final answer for this system of equations. Let's look at our fourth example. So in our fourth example, we have -2x plus 15y equals -32, and 7x minus 5y equals 17. Is there a variable right off the bat that I can eliminate if I were to add these two equations together? In this case, there is not a variable that I can eliminate right off the bat, so we have to do some changing here. We can go ahead and either make the choice to change the x's or to change the y's. I'm going to go ahead and change the y's, and I'm going to actually multiply the second equation through by 3 so that my -5y will become a -15y, and then they will cancel out. I could have eliminated the x's as well. That just would have required that I multiply both equations through by 2 numbers. So probably a 7 in the first equation and a 2 in the second equation. So the reason I decided to eliminate the y's instead is just so that I only have to change one of the 2 equations. Let's rewrite the first equation. Since I'm not changing anything in the first equation, and then in the second equation, I'm going to go ahead and multiply every single term by 3. So I'm not just multiplying the y's, I have to multiply the entire equation through by 3 so I don't change the problem. I'll get 21x minus 15y equals 51 then. From here I can add these together. -2x plus 21x will give me 19x. The y's will cancel, which was my goal, and -32 plus 51 is going to be 19. From here, I can solve for x by dividing through by 19. I'm going to start listing my final answer on the side over here, and I'm going to put a 1 in place of the x spot in our coordinate pair. Now from here, I'm going to pick one of the 2 equations, and I'll substitute in x equals 1 into that equation. I'm going to go ahead and just keep using the first equation. I could use the second, it does not matter. You should get the same answer regardless. My goal is to substitute in 1 for x, so I end up with -2 times that 1 value plus 15y equals -32. Simplifying this out, we can add 2 to both sides, and I get 15y equals -30. To get y by itself, I can divide through by 15, and y will be equal to -2. And we can go ahead and substitute that in to get our final coordinate pair. Again, just like we've talked about in the prior 2 videos, you can always check any of these problems by taking what your final answer is that you got and substituting it into both equations and making sure you get true statements. Let's look at our last example here. It says 3x plus 2y equals 1 and 4x plus 3y equals -2. Is there a variable right off the bat that if I add these together will cancel out? In this case, there's not, so we have to make the choice. Do we want to cancel the x's? Do we want to cancel the y's? I'm going to go ahead and have us cancel the x's, so my goal is now going to be to eliminate the x's, just so we can see some variety. To eliminate the x's, I'm going to need opposite coefficients here. Right now I have a 3 and a 4. They're not multiples of each other like 15 was a multiple of 5, so I only had to multiply one of the 2 equations in example 4. In example 5, 3 and 4 are not multiples, so instead I have to multiply each one. So I'm going to multiply the first equation through by 4, and then I'm going to multiply the second equation through by -3. I do need to multiply one of them through by a negative so that I have a negative and a positive. Remember, we have to distribute that to every single term. So our first equation will become 12x plus 8y equals 4. Our second equation will become -12x minus 9y equals 6. Always make sure that you're multiplying the entire equation through. Otherwise, you're going to end up changing the problem, and then we will not get the right answer. So always make sure you're multiplying every single term by whatever number you are distributing. From here, I can add these together. The x's will cancel. That was my goal, to eliminate the x's. 8y minus 9y gives me negative y, and then 4 plus 6 gives me 10. To get y by itself, divide through by negative 1, and we get that y is equal to 10. In my final answer over here, I know that I'll have 10 comma something then. My next goal is to substitute in negative 10 into either the first or the second equation. And I want to make sure I go back to the original problem so that I have my answer. So we get 3x plus 2y equals 1. So I'll use the first equation. We could use the second equation. I'm going to substitute in negative 10 in place of the y, so I'll have a negative 10 there instead. But the 3x plus 2 times the negative 10 will stay the same, still equal to 1. Simplifying, I get 3x minus 20 equals 1. If I add the 20 to the other side, I get 3x equals 21. Last step, divide through by the 3, and we get that x is equal to 7. Now I'm wondering if anybody noticed a problem that I have now. I had written my coordinate pair and I had put negative 10 in the wrong spot. We've got to make sure we're being careful here that we don't always solve for x first. So my x is 7, so I need to have the 7 in the x spot and then the negative 10 in the y spot. So just make sure you're writing it as your x comma your y coordinate always. And in all the prior examples, or most of the prior examples, we had solved for x first, so I can see why it's easy to want to write that first number you get in the x spot, but it depends on which variable it is representing. Again, make sure that if you ever want to check your answers, I could take these numbers, plug them into each of the original equations, and if I get a true statement in both, then that means that it is a solution to that system of equations. And this is the end of Learning Target 6A.